Hi, my name is Max Fortanel, and this is my electrical circuit analysis oral exam. So this exam comes from two different situations. And the first one is about our simple circuit that we can see reflected over here. So there it comes with a voltage source, a resistor, and a light emitting diode, or LED, as you may know it. And here are the specifications of this red LED that we have from the situation, which are operating voltage from 1.8 to 2.4 volts, withstand of 120 milliamps without being damaged, and a nominal current of 20 milliamps. That means that it is recommended to work with 20 milliamps of current. What we can also see from the first question that they ask us if the voltage source is 1.7 volts, what must be the value of the protection resistor R1 so that the LED is turned on with a typical voltage, the middle range voltage that we saw in the specifications, and the nominal current. So what this means is that we are going to have a voltage source of 8.7. The middle range of the typical voltage would be the half, like middle point between 1.8 and 2.4, which is 2.1 volts. And the nominal current is 20 milliamps, as we saw in the previous slide. So what I first did is calculate the voltage in the first resistor. So we know that the total voltage is equal to the voltage drops in each component from this circuit. So we know that there's an 8.7 total voltage and that the LED works with 2.1 volts. So doing this math, we can know that the voltage in the first resistor is 6.6 volts. Now using Ohm's law, BRI, we can calculate its resistance, the internal resistance from this LED, which is 2.1 divided by 20 times 10 to the minus 3, because we know that the nominal current, that will be the current that goes through that, is that 20 milliamps. So we can calculate the internal resistance from the LED, which is 105 ohms. Then using voltage dividers, we can calculate the voltage from this R1, from this. We can use voltage dividers in order to find the resistance one, as we have already the voltage in the resistor, in the first resistor, it's the total voltage, and also we have the current. So using voltage dividers, we can find, using simple math and rearranging all the factors, that the resistance in the first resistor is 329.99 ohms, which can be rounded to 330 ohms, as we can see in the corner, in the left corner, in the right corner of this image. Then we're asked that we have only two resistors, one from 220 ohms and one from 100 ohms. And then they ask us if we can build a circuit that has these same effects on the LED. So the only two ways that this can be done is in parallel or in series. What I first did is calculate the parallel option. So what we know is that in the LED has to be a current of 0.02 amps, so 20 milliamps. So we can use current dividers to calculate the total current. First of all, also we need to simplify both the parallel resistors, which is a 68.7 ohm equivalent resistor, and then we can use both current dividers to find the current that goes in the total circuit. This by rearranging, because we know that the current in the LED is 0.020 amps, and we know all the resistances, internal and the equivalent from the two parallel ones, and we can know now that the total current is 0.0505 amps. Now using again Ohm's law, we can see that the voltage from the source should be 2.10 volts in order to work this out. And that we are asking the previous slide that the voltage from the voltage source has to be 8.7 volts, not less, not more. So we can see that in parallel, it will not be possible to make a circuit that like required in question one. Then the other option is in series. We can really simply see that if we add the two resistors in series, the equivalent is 320. So it will not be possible. But if we calculate it, we know that the resistance times the current must be equal to the voltage that we are asked. and we know that the current must be 20 milliamps because they're in series, so all components have to experience the same current. So if we do this calculus, we can find that the current from the voltage source should be 8.5 volts, which is like 0.2 volts less than the circuit required in question 1. So we can see that with these two resistors, we cannot build a circuit as required in question 1. So now we can move on to the scenario number 2, which is about capacitors and in defibrillators. So we have again some specifications that tell us that the capacitors from this apparatus recharge in 10 milliseconds, and that all defibrillators used to only be able to like give up 200 energy, 200 joules of energy, but now they can deliver from 150 joules up to 360 joules, and they discharge in more or less 20 milliseconds. The first question asks us, what are the electrical variables that must be considered in order to guarantee the maximum energy delivered in a modern defibrillator? So to this, we have to understand two things. How does a capacitor circuit looks, and which are all the like the questions that model the discharge and charge from the defibrillator. So first, from the circuit that we can see above, we can notice that there is a resistance connected in series with the capacitor and the voltage source. This is due because capacitors cannot like produce energy. They work as a battery that has to be charged, or like a volt if you want to see it that way. So we need a voltage source that charges that capacitor, and the resistor that is connected in series is there in order to protect this capacitor from burning or blowing up or being damaged. So it has to be from a certain resistance in order to allow the capacitor to charge fully, but also protecting it from excess of current from a short circuit, which is where when the current is tend to be infinite, so there's no voltage and it messes things up. So the variables we need to consider in the electrical variables are the voltage from the source, which is going to affect how much energy can be stored in the capacitor, the time for discharge and charge of the capacitor, which is the time constant, or tau, which is the capacitance from times the resistance from this circuit. And as I mentioned, the resistance of this circuit has to be considered in order to be optimum for this for we to have the maximum energy delivered, and also the capacitance from this capacitor. If we have a smaller capacitor with a smaller capacitance, then we will not be able to give the maximum energy to the system or to what we want. The second question is how can we guarantee that the modern defibrillator charges in 10 seconds at most, milliseconds at most? I think there's a mistake over there. I don't know. So we need to consider that the complete charge of a capacitor is when it reaches 9.999% of its capacity. It never reaches 100 because this is like a real situation, not a perfect one, an ideal one. So capacitors will never charge up to 100%. So now that understand, we can know that the capacitors have a exponential behavior because of this. Because of in its equation, mathematically there is a exponent that makes its charge vary in an exponential way. So in order to guarantee that a modern defibrillator charges in the 10 seconds, we can have to consider tau, which is the capacitance times the resistance in this circuit. This because tau is a time constant that takes for the capacitor to charge to 63.2%. That like more than the half of, and always a capacitor will take about 5 tau to completely charge at 99.99 of its capacity. So we have to guarantee that tau is small enough or optimum enough in order to be capable of charging the defibrillator in less than 10 seconds or 10 milliseconds. I don't know if it's 10 or 10 milliseconds, but we have to consider tau in order to control how much time we take to charge the capacitor from the defibrillator. Now we are asked, how can we obtain the maximum current that is delivered to the heart during the heart rate reactivation using any defibrillator of any kind? That's, in other words, in simple words, is what are the conditions in the circuit that have to be taken to maximize the delivery of current. And talking about everything that we saw in the previous slides is like a recap. So we have to have a voltage source that can supply the maximum energy to the system, we have to have enough time for 5 tau to be reached, or a 5 tau small enough or optimum enough for we to take the time necessary to charge at maximum. And optimum resistance in the protecting the capacitor, which is also involved to tau, to prevent the damage from the capacitor, but also letting enough current to the capacitor for it to charge at full capacity, and also enough time for discharge in order to pass all the current to the body. It's not only needed the time for charging, but also the time for discharging, because if it's really small, we will not pass all the current or all the energy that we want to the patient, and we will not obtain the same result as we want. Now we are asked that to determine the power that modern defibrillators dissipates in each shock, uh, using the minimum energy that we are presented in the specifications at the beginning of this situation. So we know that the minimum energy that a modern defibrillator can supply is 150 joules, and the time of discharge is 20 milliseconds. And we also know that power is the rate of change in work or energy, how much energy is the change in energy over time. So it's a simple math calculation where we divide the 150 joules by the 20 milliseconds, and we obtain 7,500 watts or 7.5 kilowatts. So that's how we easily calculate the energy that we dissipate in each shock by a defibrillator. That's the power that we have in the modern defibrillators. Finally, we are asked on what are the factors that can prevent the patient to receive enough current in the heart to reactivate it. And we can explain this by Ohm's law. Also, we could go through the terms from biology, but we're talking about physics. So we're gonna talk about voltage, resistance, and current. So we know that because of Ohm law that voltage is equal to Ri. So I is equal to voltage divided by resistance. So what could affect the current in the body that is felt? Well, is other the voltage or the resistance in this situation. If the body has a high resistance or is a really large body and we do not give enough voltage to it, the current needed for the current that we have to feel in the heart in order to reactivate will be really small, and we will not have a reactivation, meaning that the resistance of the body is way too big for the current needed to restart the heart. Also, it could be due to the capacity of the machine, meaning that either the capacitor has not enough capacitance for the amount of energy needed to produce this current, or the voltage source is not big enough in order to give enough voltage to the capacitor to like produce this current we need to reactivate the heart. And that because we know that voltage divided by resistance is current. So if we have a small voltage and a resistance, a normal, even if it doesn't vary, it will have a small current and we will not reach the current needed for us to restart the body. Well, that will be all. I hope it's everything clear and that I fully explained everything that I talked about in this exam. And thank you for listening. And that's all. See you.